Hello there, and welcome to the Sleepy History Channel. Tonight, we are tracing the astonishing story of human evolution. This is the story of how a fragile branch of life became the only human species left on Earth. It begins long before memory. It reaches back to ancient bones, changing climates, and choices no one knew would matter. Each discovery brings us closer to a question that feels almost impossible. How did a small primate lineage become us? Human evolution is not a simple march toward the present. It is a story of chance, survival, and vanished relatives. Some of those relatives were closer to us than most people imagine. Some left traces inside living bodies today. As we move through this journey, we will follow the evidence left behind in stone, in DNA, and in the shape of the human body. Each clue reveals something startling about where we came from. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there's nothing you need to do but relax. Let your shoulders soften. Allow your breathing to slow. And as your mind begins to loosen its grip on the day, join me as we explore the deep history of humanity together. Let's begin. Your body still carries echoes from extinct human relatives. Inside many people living today are small fragments of DNA inherited from ancient relatives who disappeared long before recorded history began. These traces come mostly from Neanderthals and Denisovans. They entered our ancestry when early modern humans met and had children with these other human groups. The result is astonishing. Extinction did not erase them completely. Parts of their biology survived by becoming part of us. Some inherited variants influence immune responses. Others affect skin, hair, or how the body adapts to cold and altitude. This does not mean anyone is partly Neanderthal in a simple way. It means that human history is woven from encounters, migrations, and intimate moments between groups that once seemed separate. A tiny stretch of ancient DNA can act like a message from a vanished world. It tells us that our species did not rise in isolation. We absorbed pieces of other human stories, and those stories still move through living bodies today. Human evolution was never a ladder. It was a branching family tree. For a long time, people imagined evolution as a straight climb from ape to human. That picture is simple, but it is deeply misleading. The real story looks more like a tangled pattern of cousins, side branches, dead ends, and surprising survivors. Many ancient species had human-like traits without being our direct ancestors. Some walked upright while keeping small brains. Others developed powerful jaws or unusual bodies suited to their own environments. A few may have lived at the same time as members of our own genus. This matters because evolution does not plan ahead. It experiments through variation, and only some forms survive the pressures around them. Our lineage was not waiting at the top of a staircase. It was one branch among many. Most branches ended. One kept growing. That simple shift changes the whole feeling of the story. Humanity was not inevitable. We are the result of countless fragile turns in deep time. Several kinds of humans once shared Earth at the same time. There was a period when our planet was home to more than one humankind. Modern humans were not alone. Neanderthals lived across parts of Europe and Western Asia. Denisovans left genetic traces across Asia and Oceania. Homo floresiensis survived on an island in Southeast Asia. Other forms may have lingered in regions still poorly understood. Imagine a world where different human groups carried their own tools, habits, bodies, and ways of surviving. They were not monsters or myths. They were people in a broad biological sense, shaped by their own histories. Some likely met one another. Some exchanged genes. Others may have only shared the same century without ever crossing paths. This makes the past feel stranger than a simple origin story. For most of human evolution, being human did not mean belonging to a single species. It meant being part of a wider family, spread across landscapes that held several versions of us. The first footsteps toward humanity began in Africa millions of years ago. The earliest chapters of our story are rooted in Africa, where fossils preserve a long and complex record of changing bodies. The continent held forests, open woodlands, rivers, and shifting habitats that challenged ancient apes in new ways. Over millions of years, some lineages began moving differently. Their skulls, teeth, and limb bones reveal experiments in posture and diet. Africa was not merely a starting point on a map. It was the great stage where the foundations of humanity took shape. From there came the earliest known hominins, then later members of the genus Homo. Each discovery adds a new piece to a much older puzzle. A jaw fragment, a thigh bone, or a footprint can shift what scientists think happened next. The story is still incomplete, but one thing is clear. Long before cities, writing, or spoken histories, Africa carried the deep beginnings of the human journey in its soil. Walking upright changed our ancestors before large brains ever appeared. One of the most important human traits arrived surprisingly early. Our ancestors began walking on two legs before they developed the large brains we often associate with humanity. This turns an old assumption upside down. Intelligence did not come first and then produce a human body. Instead, a new way of moving helped reshape everything that followed. Upright walking freed the hands from constant locomotion. It changed the pelvis, spine, knees, and feet. It altered how bodies balanced, how infants were carried, and how far individuals could travel across mixed landscapes. Fossils show that some early hominins had small brains but bodies already adapted for bipedal movement. That combination is powerful because it reveals evolution working in stages. A creature could be unlike us in the head, but strangely familiar in the stride. Before the first complex tools or symbolic art, there was the simple world-changing act of standing and moving forward. Fire may have helped turn fragile humans into world travelers. A flame could make cold nights survivable, keep dangerous animals at a distance, and turn raw food into something easier to chew and digest. Cooking may have allowed our ancestors to gain more energy from the same ingredients, which mattered greatly for bodies with growing energy demands. Fire also changed the social day. After sunset, people could remain awake together in shared light. They could mend tools, watch each other, pass on knowledge, and strengthen bonds. The evidence for early fire use is debated in some places because ash and hearths do not always survive clearly. Even so, by later prehistory, fire had become a central part of human life. It was not just a tool. It was a portable environment. With it, humans could enter colder regions, alter landscapes, and carry a piece of warmth into places where biology alone might not have been enough. Neanderthals were clever, social, and adaptable. The old image of Neanderthals as dull, shambling creatures has been overturned by evidence from archaeology and genetics. They made stone tools with skill. They hunted large animals in difficult environments. They used fire, prepared hides, and lived through harsh Ice Age conditions for hundreds of thousands of years. Their bodies were strong, but strength was only one part of their success. Some sites suggest they cared for injured individuals who survived long after serious wounds. This points to social support, memory, and practical compassion. Their brains were large, though differently shaped from ours. They adapted to cold regions with broad bodies and powerful limbs. They were not failed humans waiting to be replaced. They were a sister group with their own long history. When modern humans entered their world, the meeting was not between intelligence and ignorance. It was between two capable human forms, each carrying its own inheritance of survival. The tiny finger bone revealed an unknown branch of humanity. In Denisova cave, scientists found a small bone fragment that did not look dramatic at first. It belonged to a young girl, and it was too incomplete to reveal much through shape alone. Then researchers studied its DNA, and the result changed human history. The bone did not belong to a Neanderthal or a modern human. It came from a previously unknown group now called Denisovans. This discovery was extraordinary because genetics revealed a human branch before fossils gave it a clear face. Later finds, including teeth and other fragments, added more clues. But the first breakthrough came from something so small it could have been overlooked. Denisovans are now known mostly through DNA, yet their genetic legacy appears in living populations across parts of Asia and Oceania. A tiny piece of bone opened a hidden chapter. It showed that the ground still holds human histories that our eyes alone cannot recognize. Modern humans survived because culture evolved beside biology. Our species did not succeed through anatomy alone. Biology gave us flexible bodies and remarkable brains, but culture allowed knowledge to grow beyond a single lifetime. A useful method could be taught. A route could be remembered. A tool design could be improved by the next generation. This made human survival cumulative. Instead of each person starting from nothing, communities inherited practical wisdom. Clothing, shelters, hunting strategies, food preparation, and symbolic traditions all became part of the human toolkit. Culture could also change quickly compared with genes. When climates shifted or new landscapes appeared, learned behavior could respond faster than the body could evolve. That flexibility became one of our greatest strengths. It helped humans live in deserts, cold plains, tropical forests, and coastlines. Culture turned fragile individuals into members of learning networks. In that sense, humanity became powerful not because one person knew everything, but because knowledge could move from mind to mind. Every living person belongs to one young and extraordinary species. Homo sapiens is the only human species alive today, but that loneliness is recent in evolutionary terms. For most of the deeper story, our family had company. Other human groups existed, adapted, and vanished. Our own species emerged in Africa roughly a few 100,000 years ago, which makes us young compared with the long history of life. If in that short span, we spread across the globe and reshaped nearly every environment we entered. We crossed seas, endured ice age landscapes, built languages, and created traditions that could outlast the people who began them. The extraordinary part is not that we are separate from nature. It is that nature produced a species capable of asking where it came from. Every person alive today shares that same species identity. Beneath all visible difference, there is a recent common inheritance. We are the last surviving human branch, carrying the weight of many vanished possibilities. Sahelanthropus may have walked near the edge of the human story. One of the most debated fossils in human evolution comes from Chad and is known as Sahelanthropus chadensis. It lived around 7 million years ago, close to the time when the human line and chimpanzee line may have been separating. The skull is famous because it combines a small brain case with features that some researchers interpret as possible signs of upright posture. The opening where the spinal cord enters the skull appears positioned in a way that has sparked enormous discussion. Was this creature already experimenting with bipedal movement, or was it part of a nearby branch that only resembled our ancestry? Scientists still argue about the answer. That uncertainty makes the fossil fascinating rather than less important. It sits near the shadowy border where the human story becomes difficult to distinguish from the broader ape world. Sahelanthropus reminds us that origins are rarely marked by a clean beginning. They emerge through clues. Ardipithecus had feet shaped for both branches and ground. Ardipithecus ramidus offers one of the strangest glimpses into early hominin life. This ancient species lived around 4.4 million years ago, and its skeleton shows a body caught between worlds. It could move upright on the ground, yet its foot retained a grasping big toe, useful for climbing. That combination challenges the idea that our ancestors simply left the trees and became walkers all at once. Instead, Ardipithecus suggests a more flexible life. It may have moved through woodland environments where climbing still mattered, while also using bipedal movement on land. Its hands were not shaped like those of a knuckle-walking ape, which adds another surprise. The famous fossil nicknamed Ardi revealed that early human relatives were not just primitive versions of chimpanzees. They had their own unique anatomy. In those bones, we see an experiment in movement that belongs to neither modern ape life nor fully human walking. Lucy's bones proved upright walking came before big brains. When the fossil known as Lucy was discovered in Ethiopia, she became one of the most famous individuals in deep human history. She belonged to Australopithecus afarensis and lived more than 3 million years ago. Her skeleton was incomplete, but enough remained to reveal something astonishing. Her pelvis, knee, and leg bones showed that she walked upright. Yet her brain was still much closer in size to that of an ape than to a modern human. This made Lucy a powerful answer to an old question. The human body began changing its way of moving before the brain expanded dramatically. She was small, but the implications of her bones were enormous. They showed that bipedalism was not a late feature of humanity. It was an early foundation. Lucy's remains also gave the public a rare emotional connection to prehistory. She was not just a specimen. She was an ancient life, made visible. Australopithecus afarensis left footprints that still feel startlingly human. At Litoli in Tanzania, volcanic ash captured one of the most remarkable records in paleoanthropology. More than 3.5 million years ago, individuals walked across a damp surface shortly after an eruption. The ash later hardened and preserved their tracks. The footprints are extraordinary because they reveal movement, not just anatomy. They show a foot rolling from heel to toe in a way that feels familiar. There is a clear big toe aligned with the others, unlike the grasping toe of many apes. The makers were not modern humans, and their brains were small. Yet their steps across that ancient ground look strikingly close to our own. Footprints carry a different kind of power from bones. They preserve behavior in a single moment. You can almost imagine the walkers moving across the landscape, unaware that their ordinary passage would become evidence millions of years later. Their feet left time with a human shape. The Litoli footprints preserve a family moment from deep time. The tracks at Litoli are often described scientifically, but they also invite a deeply human feeling. Several individuals crossed the same surface, and one set of prints appears to follow near another. Some researchers have wondered whether these tracks might reflect a small group moving together. We cannot know their relationship. They may not have been a family in the way we understand the word. Still, the scene is intimate because it records bodies traveling through the same place at the same time. No tool, skull, or tooth can quite match that sense of presence. These ancient walkers were not posing for history. They were simply moving through their world after ash had fallen. The softness of that surface took their weight, and geology kept the memory. The result is a rare glimpse of life rather than death. In those footsteps, deep time stops being abstract and becomes a path crossed by living beings. Some early humans had jaws built for powerful chewing. Not every relative in our ancient family was moving toward the delicate face of Homo sapiens. Some evolved in a very different direction. Certain australopiths and related forms developed massive jaws, thick enamel, and large chewing muscles. Their skulls could include flaring cheekbones and ridges where powerful muscles attached. These features suggest diets that demanded serious processing. They may have eaten tough plants, hard seeds, underground storage organs, or fallback foods used when preferred meals were scarce. The point is not that they were crude, they were specialized. Their faces were shaped by the daily challenge of turning difficult foods into energy. This path shows how evolution can solve survival problems in many ways. One lineage may become flexible and tool-oriented. Another may strengthen the machinery of the mouth. These robust forms remind us that the human family was full of alternate strategies. Some were successful for a long time, even though they eventually vanished. Paranthropus boisei earned the nickname Nutcracker Man for its huge teeth. The fossil known as Paranthropus boisei became famous because its face looked almost engineered for chewing. It had enormous back teeth, a broad face, and a powerful jaw. Early researchers gave it the nickname Nutcracker Man because the anatomy seemed perfect for cracking hard foods. Later studies complicated that story. Microscopic wear on the teeth suggests it may not have constantly eaten the hardest items available. Instead, its heavy chewing equipment may have helped it survive seasonal shortages when tough or fibrous foods became important. This is a wonderful lesson in how science changes. A nickname can capture the imagination, but evidence can refine the truth. Paranthropus boisei was not a cartoon creature built only for nuts. It was a highly adapted hominin with a body shaped by ecological pressure. Its massive teeth tell a story about survival at the edge of abundance, when the ability to chew difficult food could mean the difference between life and extinction. Not every ancient human ancestor led directly to us. Human evolution contains many species that were not steps on the path to modern people. They were relatives, not grandparents. This distinction matters. A fossil can be important, even if it did not belong to our direct line. It may show what other branches were trying, what environments demanded, or how many forms of human-like life once existed. Some species survived for long periods, then disappeared without leaving descendants. Others may be close cousins whose exact positions remain uncertain. The fossil record is uneven, and new finds can move old assumptions around. That is part of what makes the field so alive. Scientists are not filling in a neat chain. They are reconstructing a family with missing albums, misread labels, and unexpected relatives. When a species turns out not to be ancestral to us, it is not a failure. It is still a record of evolution at work. Each side branch helps reveal the wider shape of the human past. Evolution kept testing different ways to be almost human. Across millions of years, nature produced many creatures that seem familiar in one feature and strange in another. Some walked upright but had small brains. Some had human-like hands but retained climbing adaptations. Some made tools but did not look like us. Others had powerful faces, compact bodies, or unusual mixes of old and new traits. These combinations can feel puzzling because we are used to seeing ourselves as the final package. Evolution does not work that way. Traits appear in mosaics. They spread, change, or disappear depending on whether they help in a particular setting. Being almost human was not one condition. It was many experiments unfolding across different landscapes and times. This makes the past feel wonderfully crowded with possibility. A fossil jaw, a foot bone, or a stone tool may represent a path that came close to us without becoming us. Our species emerged from this long period of trial, not from a single straight design. Homo habilis may have carried tools into a new age. Homo habilis is often linked with some of the earliest stone tool traditions, although the full picture remains debated. Its name means handyman, and that name reflects the excitement researchers felt when fossils appeared near ancient tools. The species lived more than 2 million years ago and had a brain larger than many earlier hominins, though still far smaller than ours. What makes it captivating is the possibility that tool use was becoming more central to survival. Sharp flakes could cut meat from bones, slice plants, and open resources that teeth alone could not handle as efficiently. Tools created new relationships between hand, eye, and mind. They also changed how food could be shared or processed. Homo habilis stands near a threshold where technology began to matter in a deeper way. It was not modern invention, but it was a beginning. A struck stone could turn a small primate into a more flexible survivor. Stone tools changed hands, diets, and the future of survival. A sharp edge may seem simple, but in the hands of an early human, it opened a new relationship with the world. Stone flakes could slice through hide, separate meat from bone, and cut plant material that fingers and teeth could not manage as well. This changed what our ancestors could eat. It also changed how they used their bodies. Hands became instruments of precision. Eyes learned to judge angles. Minds began linking a blow in the present with a useful edge in the future. A stone tool is not just an object. It is a plan made solid. Once early humans learned to make and carry cutting tools, they were no longer limited to what the body alone could do. They could reach into carcasses, process tougher foods, and solve problems outside the moment. In that quiet leap, survival began to depend not only on muscle and instinct, but on memory, skill, and teaching. Oldowan tools were simple stones with world-changing consequences. The earliest, widely recognized stone tool tradition looks plain at first glance. A rounded stone was struck with another stone to create sharp flakes. The result could fit in the palm, but it changed the scale of possibility. Oldowan toolmakers did not need metal, fire-hardened points, or elaborate workshops. They needed the right rock, a controlled strike, and the ability to recognize a useful edge before it existed. These tools helped early humans cut food, scrape surfaces, and open access to resources that were otherwise difficult to reach. The brilliance lies in the simplicity. A single flake could do work that teeth and nails could not. Archaeologists find these artifacts scattered across ancient sites, often near animal bones with cut marks. That pairing tells a powerful story. Something with a small brain by our standards was already changing the world through technique. The Oldowan was not crude failure. It was the first great industrial whisper. Acheulean hand axes remained useful for over 1 million years. Some inventions vanish quickly. Others are so effective that they endure beyond imagination. Acheulean hand axes belong to the second kind. These shaped stone tools appeared more than 1 million years ago and remained in use for an extraordinary span of time. Their makers carefully chipped both sides to create a strong, balanced edge. Many have a teardrop shape that still feels deliberate in the hand. They could butcher animals, cut wood, scrape hides, and handle many tasks with one durable design. What makes them so fascinating is not only their usefulness, but their consistency. Across huge distances and countless generations, ancient humans returned to the same basic form. That suggests teaching, attention, and a shared sense of what worked. Holding one today can feel surprisingly intimate. You are touching a design that outlasted entire species, survived changing climates, and carried practical intelligence through a stretch of time almost too large to imagine. Homo erectus became the first great human traveler. At some point, one human species moved beyond Africa and began a wider journey across the Old World. Homo erectus had a body suited for distance. Its legs were long, its posture was upright, and its proportions were more familiar than those of earlier hominins. Fossils and tools linked to this species or its close relatives appear across parts of Africa, Asia, and Europe. This expansion did not happen as a single heroic migration. It likely unfolded slowly, generation after generation, as groups followed water, food, and opportunity. What makes it astonishing is the scale. These were not modern people with maps or written language. They entered unfamiliar lands through endurance, observation, and adaptation. Their movement widened the human world forever. For the first time, our family was no longer tied to one continent. The horizon itself became part of the human story, and ancient feet carried that story into landscapes no hominin had known before. Homo erectus may have walked with a stride much like ours. When scientists study the bones of Homo erectus, one feature stands out. This ancient human species was built for efficient walking. The legs, hips, and feet suggest a body that could move across long distances with a rhythm recognizable to us. Earlier hominins often retained stronger climbing adaptations, but Homo erectus looks more committed to life on the ground. That change matters because movement shapes destiny. A body that travels well can follow migrating animals, reach new water sources, and spread into new habitats. The famous Narration boy skeleton revealed long limbs and a narrow body form suited to heat loss and endurance. Its anatomy shows that ancient humans were becoming walkers of the open world. Imagine the power of that shift. A creature no longer bound closely to trees could cross plains, explore coastlines, and keep going beyond familiar territory. The human journey became longer because the human stride became better. Human noses may have helped condition air during long journeys. The human nose is more than a feature on the face. It is a small climate system at the entrance to the body. As air passes through the nasal passages, it can be warmed, moistened, and filtered before reaching the lungs. This matters for a species that spread into many environments. Cold air can irritate delicate tissues. Dry air can pull moisture from the respiratory system. A projecting external nose may have helped manage those challenges, though scientists still debate the exact evolutionary pressures involved. Its shape varies widely among populations, and some of that variation may reflect long histories in different climates. The nose also supports smell, speech resonance, and breathing during exertion. It sits in the middle of the face so familiarly that we forget how strange it is among apes. Yet this everyday structure may carry evidence of ancient journeys, when breathing well helped bodies endure new kinds of air. Running may have shaped our hips, tendons, and cooling skin. Humans are not the fastest animals, but we are surprisingly good at covering distance. Some researchers argue that endurance running influenced parts of our anatomy. The springy arch of the foot can store energy. The Achilles tendon can act like an elastic cord. The large gluteal muscles help stabilize the trunk when the body pitches forward with each stride. Even the head has features that may help keep vision steady while moving. None of this means our ancestors were built only for running. Evolution rarely works so neatly. But the human body does show a remarkable ability to travel at moderate speed for a long time. In hot conditions, that can become powerful. Many prey animals sprint beautifully, then overheat or tire. A human group moving steadily, tracking carefully, and cooling effectively could turn patience into strategy. The story of running is not about speed alone. It is about persistence becoming a form of strength. Sweating turned humans into strangely effective long-distance hunters. Most mammals cool themselves by panting, which can interfere with breathing during intense movement. Humans do something different. We sweat across much of the skin, and evaporation carries heat away from the body. This is costly because it uses water and salt, but it allows activity to continue in conditions where other animals may struggle. Paired with upright posture, reduced body hair, and careful tracking, sweating may have helped some ancient humans hunt by endurance. The idea is called assistance hunting. A group could follow an animal through heat until the animal became exhausted. This strategy is rare, but it has been documented among some modern foragers. Whether it was common in prehistory is debated, yet the physiology remains remarkable. The human body can turn heat loss into a survival advantage. We are soft-skinned, slow compared with many predators, and physically vulnerable. Yet under the right sun, our cooling system becomes a hidden weapon. Losing thick body hair helped our ancestors survive under heat. Compared with other apes, humans are unusually bare. We still have hair follicles across the body, but the thick fur covering was greatly reduced in our lineage. One leading explanation connects this change to heat management. A less hairy body allows sweat to evaporate more effectively, which helps cool the skin during exertion. For ancestors moving through warmer, more open environments, that could have been crucial. Losing fur may also have changed social life and protection. Skin became more exposed to sunlight, insects, and injury. This likely created new pressures involving pigmentation, clothing, shelters, and grooming behavior. The transition was not simply cosmetic. It altered how the body met the world. Our skin became a surface for cooling, signaling, touch, and protection. The absence of dense fur is so familiar that it seems ordinary. In evolutionary terms, it is one of the strangest human traits, and it helped make endurance possible. Dark skin evolved as protection beneath intense equatorial sunlight. Human skin color is deeply connected to sunlight. Near the equator, ultraviolet radiation is strong enough to damage folate, an important nutrient involved in cell division and reproduction. Darker pigmentation, produced by melanin, helps shield the body from that damage. This adaptation would have mattered greatly for early humans living under intense sun with reduced body hair. Melanin also protects deeper skin structures from harmful radiation while still allowing the skin to function as a living organ. The story is not about race in the social sense. It is about biology responding to environment across generations. Dark skin was likely an early and essential human adaptation, especially once the body became more exposed. It helped our ancestors survive in bright landscapes where heat and radiation were daily realities. Seen this way, skin is not a simple surface. It is a record of ancient sunlight, written by natural selection into the bodies of living people. Lighter skin later helped some populations make vitamin D. When humans moved into regions with weaker sunlight, a new challenge appeared. The body needs ultraviolet light to help produce vitamin D, which supports bone health and other vital processes. In places far from the equator, especially during long winters, too much melanin could reduce vitamin D production. Over many generations, some populations evolved lighter skin, which allowed more ultraviolet light to penetrate. This did not happen in one way or at one time, everywhere. Diet, latitude, clothing, and cultural habits all shaped the pressures involved. Some northern groups retained darker skin while obtaining vitamin D from marine foods. Others evolved lighter pigmentation through different genetic routes. The result is a beautiful example of evolution's flexibility. Skin color changed as people entered new environments and found different solutions to the same biological need. It reminds us that human variation is not a hierarchy. It is a map of adaptation under changing skies. Human eyes reveal unusual amounts of white for social signaling. Look at a human face, and the direction of attention is often easy to read. The white part of the eye, called the sclera, is unusually visible in our species. In many other apes, the contrast between iris and surrounding tissue is less obvious. This difference may help humans follow one another's gaze with remarkable precision. That ability matters in social life. A glance can show interest, warning, surprise, or shared attention without a word. It can guide a child toward an object, coordinate a hunt, or reveal what someone else has noticed. Human communication is not only speech. It is also a world of small signals that pass across the face. The eye may have become part of our cooperative toolkit. A visible gaze makes thoughts slightly more public. It allows minds to meet in tiny movements. In that sense, the whites of our eyes may hold part of the story of human trust. Our hands became tools for touch, craft, and communication. The human hand is one of evolution's great instruments. It can grip a branch, cradle an infant, shape a stone, thread a needle, or express meaning without sound. Its power comes from a balance of strength and sensitivity. The fingertips are packed with nerve endings that can detect texture, pressure, and tiny changes in shape. The fingers can work together or separately, allowing delicate control. This makes the hand more than a mechanical device. It is a bridge between the mind and the world. When early humans shaped materials, the hand carried intention into wood, bone, hide, and stone. When they gestured, it carried meaning between people. The same anatomy that can hold a hammer can also comfort another person. That range is extraordinary. Human hands did not evolve for one task alone. They became flexible partners in survival, thought, and social life, turning imagination into action one movement at a time. Opposable thumbs help turn ideas into objects. The thumb may be small compared with the whole body, but its importance is enormous. Its ability to meet the fingers gives the hand a precise grip. This makes it possible to pinch, rotate, press, and control objects with fine detail. Other primates also have useful thumbs, but the human thumb is especially powerful relative to the fingers. It helps us hold a stone core while striking it, guide a needle through material, or twist fibers into cord. A thought in the mind becomes useful only when the body can carry it out. The thumb helped close that gap. It gave early humans a way to transform raw materials into tools, ornaments, containers, and countless later inventions. Even a simple gesture depends on this anatomy. Touch your thumb to each fingertip, and you are feeling an ancient adaptation at work. In that little arc of movement, possibility becomes practical. The human shoulder still remembers an ancestor built for climbing. Our shoulders are wonderfully mobile. You can lift an arm overhead, reach behind your back, throw, hang, and rotate in ways many mammals cannot. This flexibility carries traces of an arboreal past, when ancient relatives moved through trees and needed arms capable of wide motion. Later, the same inherited structure found new uses. In humans, the shoulder became important for throwing, tool use, carrying, and gesture. This is a classic evolutionary theme. A body part shaped under one set of conditions can be repurposed under another. The shoulder also comes with trade-offs. Its mobility makes it more vulnerable to dislocation and strain than a more locked-down joint. That vulnerability is part of the price of range. Every time a person throws a spear, lifts a child, or reaches for something above them, they are using anatomy with deep roots. The shoulder is not a clean modern design. It is history in motion. Childbirth became more difficult as brains and walking evolved together. Human birth reflects a remarkable evolutionary compromise. Upright walking changed the shape of the pelvis, while increasing brain size made newborn heads larger. These pressures pulled anatomy in different directions. A pelvis too wide could affect efficient movement. A birth canal too narrow could make delivery dangerous. The result is a complex passage that human infants navigate through rotation during birth. Compared with many other primates, human childbirth can be especially demanding. This difficulty may have helped shape social behavior. Assistance during birth, shared knowledge, and support from others could improve survival for both mother and child. It is a powerful reminder that evolution does not produce perfect solutions. It produces workable balances. The same changes that helped our ancestors walk far and think deeply also made arrival into the world more complicated. Human life begins with evidence of our evolutionary history already present in the body before a first breath is even taken. Human babies are born unusually helpless compared with other apes. A newborn chimpanzee can cling strongly to its mother's fur. A human newborn cannot do anything like that. Our babies arrive with limited movement, poor coordination, and a brain still undergoing enormous development. This helplessness is not a weakness by itself. It is part of a larger strategy. Because so much brain growth continues after birth, infants enter a world rich with social information while their nervous systems are still forming. They learn voices, faces, rhythms, and emotional patterns from the beginning. This long dependency demands care, but it also creates opportunity. Human development unfolds inside relationships. A baby's mind is shaped not only by genes, but by touch, speech, attention, and shared routines. The cost is high for caregivers, yet the payoff is extraordinary flexibility. Instead of being born with every behavior fixed, humans are born ready to absorb a culture. Our helpless beginning helps explain our astonishing capacity to learn. Long childhood gave human brains time to learn culture deeply. Human childhood lasts a very long time. Compared with many animals, we spend years growing, watching, practicing, failing, and trying again before full independence. This slow development may seem inefficient, but it allows something remarkable. Children can absorb complicated skills that would be impossible to master quickly. They learn language, social rules, tool use, food knowledge, and the habits of their community. Play becomes rehearsal for adult life. Curiosity becomes a survival tool. A long childhood also gives the brain time to build flexible networks shaped by experience. This means humans are not locked into one narrow way of living. A child born into a fishing community, a farming village, or a mobile foraging group can grow into the knowledge needed there. Biology creates the learner, while culture supplies the content. In that extended period of dependence, human societies place their future inside young minds, then slowly teach those minds how to carry it forward. Grandparents may have helped human families grow more resilient. Humans are unusual because many people live long after their reproductive years. One explanation is the grandmother hypothesis, which suggests that older adults help descendants survive by providing food, knowledge, and care. In foraging societies, skilled elders may know where resources appear, how seasons change, and which plants are safe. They can help feed children, allowing mothers to recover, gather, or care for additional offspring. This support may have increased the survival of grandchildren, which would make longevity beneficial in an evolutionary sense. The idea is not limited to grandmothers in a narrow modern role. It points to the wider value of experienced older people. In a species dependent on learning, memory is survival. An elder can carry decades of observation about droughts, injuries, animals, and social bonds. Long life becomes more than personal endurance. It becomes a resource for the group, turning age into a form of inherited strength. Shared childcare may have shaped human kindness and cooperation. Human children require so much care that raising them alone would have been extremely difficult through much of our past. Anthropologists use the term cooperative breeding to describe systems where individuals beyond the mother help care for young. In humans, that help can come from fathers, siblings, grandparents, relatives, and trusted group members. This pattern may have shaped our emotional lives. Babies who depend on several caregivers need to attract attention, read faces, and respond to social signals. Adults who help with children benefit from patience, empathy, and sensitivity to need. Over generations, the demands of childcare may have strengthened the importance of cooperation. A helpless infant could become a center of social bonding, pulling a group into shared responsibility. This does not mean humans are always kind. It means kindness has deep practical roots. Our capacity to nurture may be tied to one of the hardest survival problems our species ever faced. Cooking made food softer, safer, and easier to digest. Cooking is a biological game changer because it begins digestion outside the body. Heat softens tough fibers, breaks down starches, and makes many foods easier to chew. It can reduce pathogens and neutralize some toxins. For early humans, that meant more usable energy from meals and less strain on teeth and intestines. A cooked tuber, roasted meat, or softened plant can feed the body more efficiently than the raw version. Some researchers have argued that cooking helped support changes in human anatomy, including smaller teeth and a less bulky gut. The timing of habitual cooking is still debated, but its importance is undeniable. Once fire became a regular part of food preparation, humans gained a powerful new tool for survival. Cooking also changes flavor, smell, and sharing. A meal can draw people together around a hearth. In that moment, chemistry, nourishment, and social life meet. Food becomes not just found, but transformed. Firelight may have lengthened human evenings into time for stories. Before artificial light, darkness changed everything. A controlled flame could extend the usable day after sunset. Around fire, people could remain close, alert, and socially connected when the landscape beyond was harder to navigate. This extra time may have mattered for communication. Evening hours are well suited to storytelling, teaching, planning, and remembering. In many traditional societies, firelit gatherings are settings where knowledge is passed through speech. Myths, warnings, roots, animal behavior, and moral lessons can all travel through narrative. We cannot recover the first stories, but we can imagine why the setting mattered. Fire creates a circle of visibility. Faces become readable. Voices carry. Children listen while adults speak. The flames do not merely provide light, they create a social space. In that space, memory can become shared history. Long before writing, the evening hearth may have helped turn experience into culture, and culture into something that could survive the speaker. Controlled fire changed landscapes long before farming ever began. Humans did not wait for agriculture to influence ecosystems. Once people learned to use fire deliberately, they could shape the land in powerful ways. Burning can clear undergrowth, encourage fresh plant growth, flush animals from cover, and reduce the risk of larger, uncontrolled fires. Many indigenous traditions around the world have used careful burning to maintain productive landscapes. The deep history of such practices is difficult to trace in detail, but it is clear that human fire use became an ecological force long before ploughed fields and permanent villages. This changes the way we imagine ancient people. They were not simply wandering through untouched wilderness. In some places, they were active managers of their surroundings. Fire could turn dense vegetation into more open habitat, guide animal movement, and renew useful plants. A flame held in the hand became a tool of landscape design. With it, humans began shaping nature before they ever built farms. Meat-eating gave some ancestors access to dense energy. Animal foods offered early humans concentrated calories, fat, and protein. This mattered in environments where survival depended on making the most of every opportunity. Meat could come from hunting, scavenging, or a mixture of both. Even a carcass left by a predator might contain valuable tissue if a group had sharp tools and the courage to approach. Cut marks on fossil bones show that ancient humans were processing animal remains very early in the story of our genus. Meat was not the only important food, and humans have always been dietary generalists. Still, animal foods may have supported larger bodies, wider-ranging movement, and demanding brain tissue. The key point is flexibility. A creature that can eat fruit, roots, seeds, marrow, and meat has more ways to survive than one tied to a narrow menu. Meat eating added another powerful option. It helped early humans turn risk, skill, and timing into nourishment. Marrow cracking revealed intelligence hidden inside abandoned bones. Long after the obvious meat was gone, bones could still contain treasure. Marrow is rich in fat, and fat is extremely valuable for hungry bodies. To reach it, early humans had to break open bones with stoves. That required recognizing hidden food inside a hard object. It also required force, aim, and the right tool. Archaeological sites with fractured bones and stone artifacts suggest that ancient humans learned to exploit this resource. This behavior is fascinating because it shows a mind working beyond the surface. The reward was invisible until the bone opened. In a competitive environment, that could matter. Predators might take the flesh first, but marrow could remain sealed away. A hominin able to recover it gained calories that others missed. This is not just feeding. It is problem-solving with a delayed payoff. Inside those cracked bones, we glimpse a practical intelligence that could turn leftovers into survival. Humans learned to thrive by eating almost anything available. One of the great strengths of the human lineage is dietary flexibility. We are not built for a single narrow food source. Across the world, humans have lived on diets centered around plants, meat, fish, grains, tubers, dairy, insects, and countless local combinations. That flexibility has deep evolutionary roots. Ancient humans faced changing climates and shifting habitats. A group that could switch foods when conditions changed had a better chance of survival. Tools, cooking, sharing, and knowledge all expanded the menu. A bitter plant might become edible after processing. A shellfish bed could feed a coastal group. A seasonal fruit could be remembered and revisited. Food knowledge became a form of intelligence stored in culture. The human body also adapted in different populations, but behavior often moved faster than genes. Our success came from not being trapped by one menu. We became specialists in versatility, able to make a living from almost any landscape. Teeth preserve menus from lives that vanished long ago. Teeth are among the most durable parts of the body. and they carry extraordinary evidence. Their shapes reveal chewing demands. Their wear patterns show whether food was gritty, tough, or processed. Tiny scratches and pits on enamel can preserve clues from meals eaten shortly before death. Chemical signatures inside teeth can reflect the kinds of plants or animals a person consumed during growth. Even tartar, which forms from hardened dental plaque, can trap microscopic remains of food. Because teeth develop in stages, they can also record childhood conditions in ways bones may not. This makes them time capsules. A molar from an ancient jaw is not just a chewing surface. It is a biography in mineral form. Through teeth, scientists can investigate diets, migration, stress, and adaptation. The vanished individual cannot speak, but the enamel remains. It tells us what passed through the mouth, and sometimes what kind of world surrounded that life. Ancient plaque can reveal meals, medicines, and hidden microbes. Dental plaque seems ordinary and unpleasant, but when it hardens into calculus, it can preserve a microscopic archive. Ancient calculus can trap starch grains, plant fibers, pollen, proteins, and traces of microbes. Scientists have used it to study what past humans ate and what bacteria lived in their mouths. In some cases, it has revealed plant use that would otherwise leave little archaeological evidence. There are even clues suggesting that ancient people may have chewed plants with medicinal properties. This is remarkable because it turns a dental nuisance into one of archaeology's richest sources. Tools and bones show part of survival. Plaque can show the intimate details of daily life. It can preserve what people placed in their mouths or grew on their teeth, and how oral ecosystems changed with diet and culture. A hardened fleck on an ancient tooth can contain a whole hidden world, small enough to miss and valuable enough to transform a story. Fossil bones can record growth, like rings inside trees. Bones may look solid and silent, but they can preserve patterns of growth. Under a microscope, fossil bone tissue reveals structures that show how fast an animal grew when growth slowed and how the body repaired itself. In ancient humans, this evidence helps scientists compare development across species. Some grew quickly, more like apes. Others show slower patterns that edge closer to the long childhood seen in modern humans. Teeth provide especially precise developmental records because enamel forms in rhythmic layers. These biological clocks can reveal age at death and pace of maturation. This matters because growth is tied to life history. A species that matures slowly may depend on longer care, deeper learning, and stronger social support. A fossil bone is therefore more than a shape for classification. It can hold the tempo of a vanished life. In its microscopic structure, the body left behind a record of time passing from the inside. The human brain grew through pulses rather than steady progress. Brain evolution was not a smooth upward climb. Across the human family, brain size changed unevenly, with periods of relative stability and periods of expansion. Some species with small brains walked upright successfully for long spans. Later members of Homo show larger brains, but not all at once, and not always in a simple sequence. Environmental change, social complexity, diet, tool use, and developmental shifts may all have influenced the pattern. A bigger brain also came with costs. Brain tissue uses a great deal of energy, and childbirth became more challenging as heads enlarged. This means expansion had to be worth its price. The fascinating part is that there was no single switch that made us intelligent. Instead, the brain changed to a long series of pressures and opportunities. Some branches experimented with different body plans. Others invested more in neural capacity. Our own mind is the result of that uneven history, not a straight line of improvement. brain size alone never explains intelligence in human evolution. It is tempting to rank ancient humans by brain volume, but that can mislead us. Intelligence depends on organization, connectivity, development, body size, social learning, and how a brain is used within a culture. Neanderthals had large brains, yet their brain shape differed from ours. Some smaller-brained hominins may have shown surprisingly complex behavior for their size. Even modern animals remind us that cleverness is not measured by bulk alone. Birds with tiny brains can solve difficult problems. Elephants and dolphins show intelligence shaped by very different bodies and lives. In human evolution, brain size matters, but it is only part of the story. A brain also needs time to learn, hands to act, senses to guide it, and a community to supply knowledge. The most important human achievement may not be raw brain volume. It may be the ability to link minds together through teaching, imitation, memory, and shared meaning. Social life may have pushed human minds toward greater complexity. A lonely animal needs skill, but a social animal needs strategy. Early humans had to remember faces, judge intentions, manage alliances, notice tension, and learn from others. Those demands may have placed powerful pressure on the mind. In a group, survival is not only about finding food or avoiding danger. It is also about knowing who can be trusted, who needs help, and who might share knowledge. Social living rewards memory, empathy, prediction, and self-control. A smarter brain can track relationships across time. It can learn from a gesture, a glance, or a warning sound. This may have helped human intelligence grow in a distinctly social direction. Our minds became tuned not just to landscapes, but to one another. The result is a species that can cooperate with relatives, strangers, and even people who will never meet. That ability begins with ancient pressures inside small groups, where understanding another mind could change a life. Language left no fossils, but it reshaped everything. No archaeologist can dig up the first sentence. Spoken language vanishes as soon as breath leaves the mouth. Yet its effects are everywhere in the human story. With words, knowledge can move far beyond what gesture alone can carry. A person can describe a distant water source, warn of a hidden danger, explain a tool-making step, or tell a child about something that happened before they were born. Language makes absent things present in the mind. It allows planning, teaching, bargaining, joking, memory, and shared identity. Scientists look for indirect clues in anatomy, genetics, brain organization, and archaeology, but the exact beginning remains unknown. That mystery is part of its power. At some point, sound became structured meaning. Once that happened, culture could grow at a breathtaking pace. A spoken word is invisible, but it may be one of the strongest forces evolution ever placed in human hands. The hyoid bone hints at voices from vanished human relatives. Deep in the throat sits a small horseshoe-shaped bone that helps support the tongue and plays a role in speech. It is called the hyoid, and it has become one of the most intriguing pieces of evidence in the study of ancient voices. A Neanderthal hyoid found at Kibara Cave looks remarkably similar to that of modern humans. By itself, that does not prove Neanderthals spoke as we do. Speech depends on the brain, breath control, hearing, mouth shape, and social use. Still, the bone suggests that at least part of the vocal machinery was present. This is fascinating because sound rarely survives in the fossil record. We cannot hear a Neanderthal call across a valley or listen to a Denisovan child learning from adults. But anatomy can leave hints. The hyoid offers a small, delicate clue that some vanished relatives may have lived in worlds shaped by complex vocal communication. FOXP2 became famous for its link to speech. A single gene does not create language, but one gene became famous because of its connection to speech and communication. FumACP2 helps regulate other genes involved in brain development and motor control. Scientists first noticed its importance through a family with inherited difficulties in speech and language. Later, researchers found that modern humans and Neanderthals shared a version of this gene linked to fine control of mouth and face movements. This discovery caused excitement because it offered a biological clue to a deeply human ability. The story is more complicated than early headlines suggested. Language is not produced by one genetic switch. It depends on networks of genes, learning, culture, and social life. Even so, FOXP2 remains a powerful reminder that speech rests on physical foundations. Every sentence requires breath, timing, muscle control, memory, and meaning. Behind ordinary conversation lies an ancient biological orchestra, tuned through evolution and practiced through childhood. Music may have been part of human life before writing. Long before anyone recorded a law, a harvest, or a royal name, humans may have made rhythm and melody. Music leaves few traces, but its deep presence in every known culture suggests ancient roots. A beat can coordinate movement. A psalm can soothe an infant. A shared melody can strengthen belonging among people who gather in the same space. Music also reaches emotion quickly, often before words are fully understood. For early humans, that power may have mattered. It could help groups move together, remember stories, or mark moments of importance. The body itself is musical in a basic sense. We walk in rhythm, breathe in patterns, and respond to repeated sound. Archaeological finds show that people were making instruments deep in the Ice Age. That means ancient minds were not focused only on food and danger. They also created sound for meaning, feeling, and connection. Music may be one of humanity's oldest social technologies. The oldest known flutes were carved from bone and ivory. In caves of southwestern Germany, archaeologists found instruments that still seem astonishing today. Some were made from bird bones. Others were carved from mammoth ivory, a far more difficult material to shape. These flutes are more than 40,000 years old, and they show that Ice Age people had the skill to create controlled sound. A flute requires planning. Holes must be placed carefully. The maker has to understand the material, the hollow space, and the breath that will pass through it. These were not crude noisemakers. They were objects of craft and intention. Imagine a small group inside a shelter as music rises from a carved bone. The same landscape held cold, risk, and hunger, yet people still made instruments. That fact is deeply moving. It tells us that early modern humans carried more than survival knowledge. They carried rhythm, curiosity, and the desire to shape air into something worth hearing. Cave art shows minds capable of memory, symbol, and imagination. Deep inside caves, ancient artists painted animals, signs, and mysterious forms in places far from daylight. These images are not random marks. Many show careful observation, confident lines, and a strong sense of movement. Horses seem to gallop. Bison appear massive and alive. Hands pressed against rock leave the outline of a person who stood there thousands of years ago. Cave art matters because it reveals a mind capable of holding an image internally, then placing it onto a surface for others to see. That is a remarkable leap. The artwork may have carried ritual meaning, teaching value, social identity, or something we cannot recover. Its full purpose remains debated, but its existence is enough to change how we see ancient people. They were not simply enduring the Ice Age. They were interpreting the world. In darkness beneath the ground, they turned memory into marks, and those marks still speak across deep time. Red ochre may be among humanity's oldest symbolic materials. Before written signs and painted cave walls, people were collecting and using red ochre. This iron-rich mineral can be ground into pigment, and it appears at ancient sites across Africa and beyond. Its color is striking, and it can be used on skin, tools, shells, or surfaces. The meaning of ochre use is not always clear. Sometimes it may have had practical uses, such as hide treatment or adhesive mixtures. In other cases, its careful collection and processing suggest symbolic behavior. Red is a powerful color because it is linked visually to blood, warmth, and life, though we cannot know exactly what ancient people thought it meant. What we can say is that ochre shows attention beyond immediate survival. Someone chose it, carried it, ground it, and applied it. That sequence turns a mineral into a message. In a small trace of red dust, we glimpse the early human urge to mark the world. Beads reveal ancient people cared about identity and belonging. A shell bead may be tiny, but its meaning can be enormous. Archaeologists have found ancient beads made from shells, teeth, eggshell, and other materials. Many show signs of drilling, stringing, and wear. That means they were not just collected. They were displayed on bodies, clothing, or belongings. Personal ornaments reveal something profound about ancient minds. A bead can say who someone is, where they belong, or what role they hold. It can connect people within a group or signal difference between groups. It can also carry memory through touch and use. Unlike a cutting tool, an ornament does not help slice food or scrape hides directly. Its power is social. It works because other people understand it. This suggests communities with shared meanings, recognized styles, and perhaps long-distance exchange. When early humans wore beads, they were doing something deeply familiar. They were using objects to make identity visible. Burial practices suggest some early humans treated death with meaning. Death is biologically simple, but human responses to it are anything but simple. Archaeological evidence suggests that some ancient people placed bodies in ways that may reflect care, memory, or ritual. Interpreting burials is difficult because natural processes can move bones and create misleading patterns. Still, certain sites show bodies positioned deliberately, sometimes associated with tools, pigments, or other materials. These acts hint that death was not always treated as mere disposal. A body might be protected, remembered, or given a place. That possibility is powerful because it points toward emotional and symbolic life. To bury someone is to act for a person who can no longer act back. It requires memory and perhaps belief. We cannot enter the minds of those who performed these acts, but we can feel the weight of the gesture. In the treatment of the dead, ancient humans may have revealed how deeply they understood attachment. Neanderthals cared for injured companions who could not survive alone. Some Neanderthal skeletons show severe injuries that healed long before death. There are individuals with damaged limbs, missing teeth, poor mobility, and signs of lasting physical hardship. Survival with such conditions would have been difficult in Ice Age environments. A person who struggled to hunt, chew, or move efficiently may have needed food, protection, and tolerance from others. This evidence suggests that Neanderthal groups sometimes supported vulnerable members. That is one of the most humanizing things we know about them. Fear is not preserved as a soft emotion in the ground. It appears through healed bone, a fracture that mended, a toothless jaw that kept living, a body that endured years after trauma. These clues show that Neanderthal life was not only competition. It included dependence and response. Their world may have been harsh, but within it were relationships strong enough to help injured individuals continue living. Neanderthals made tools before modern humans reached Europe. Long before modern humans became established in Europe, Neanderthals had developed sophisticated tool traditions of their own. They shaped stone using prepared core techniques that required planning several steps ahead. A toolmaker had to imagine the flake before striking it. The core had to be shaped so that a useful edge would detach at the right angle. This was not random smashing. It was controlled production. Neanderthals made scrapers, points, and cutting tools suited to their needs. Some may have hafted stone pieces onto handles using adhesives, which adds another layer of technical skill. Their tools helped them process animals, prepare hides, work wood, and survive in demanding environments. This matters because technology was not a gift brought to passive relatives by our species. Neanderthals already had their own intelligence expressed through craft. When modern humans arrived, they encountered people who understood stone, fire, landscape, and survival through long experience. Some Neanderthals used pigments, feathers, and possibly personal ornaments. Evidence from several sites suggests that Neanderthals may have decorated themselves or their belongings. Pigments appear in contexts linked to their occupations. Bird bones with cut marks suggest that feathers or claws may have been intentionally removed. Some shells and other objects have been interpreted as ornaments, though debates continue over details. The important point is that Neanderthal behavior cannot be reduced to basic survival. They may have cared about appearance, display, and shared meaning. Ornamentation matters because it requires an audience. A colored object or feather has value when others notice it and understand something about it. Even if the exact message is lost, the behavior suggests social worlds with nuance. It also narrows the imagined gap between them and us. The more evidence appears, the less Neanderthals look like a simple contrast to modern humans. They become something more interesting. They were another humanity, with their own ways of making life meaningful. Neanderthal bodies were powerfully built for Ice Age survival. A Neanderthal standing beside a modern human would look familiar, but not identical. Their bodies were generally shorter, broader, and more muscular. Their chests were wide. Their limbs were sturdy. This build suited cold climates because compact bodies conserve heat more effectively than long, narrow ones. Strength also mattered in close-range hunting and rugged terrain. The bones show heavy muscle attachments, which suggest physically demanding lives. Many skeletons carry injuries that resemble patterns seen in people who work with large animals or face repeated impacts. Their anatomy was not primitive. It was adapted. A thick body, strong hands, and powerful arms were practical solutions to a difficult world. The Ice Age was not a backdrop. It was a force shaping bodies generation after generation. Neanderthals endured glacial Europe and Western Asia for a very long time. Their form tells a story of cold air, hard work, and survival through strength. Their large noses may have helped warm freezing air. Neanderthal faces had prominent noses and a projecting midface, and scientists have long wondered why. One possibility is that their nasal passages helped condition cold, dry air before it reached the lungs. In freezing environments, breathing is not a minor detail. Air must be warmed and moistened, especially during activity. A large internal nasal region may have supported that process. There are other interpretations too, including links to overall facial growth and body size. The debate remains active, which makes the feature even more intriguing. A nose can be shaped by several pressures at once. In Neanderthals, it sits at the meeting point of climate, breathing, and skull architecture. This reminds us that faces are not just expressions. They are functional landscapes. The Neanderthal face carried the demands of a cold world in bone. Every breath they drew passed through anatomy shaped by thousands of winters. Neanderthal DNA still affects immunity in many people today. When modern humans interbred with Neanderthals, some inherited genetic variants proved useful enough to remain in later populations. Several of these variants are linked to immune function. That makes sense, because groups entering new regions encountered unfamiliar pathogens. Neanderthals had lived in parts of Eurasia for hundreds of thousands of years, so their immune systems had already been shaped by local disease environments. When modern humans acquired some of those variants, they may have gained faster adaptation than waiting for new mutations to arise. This is one of the most striking examples of ancient contact-shaping living biology. A meeting between two human groups long ago can still influence how immune systems respond today. Not every inherited variant is helpful in every setting. Some may raise risks under modern conditions. Evolution has no perfect foresight. Still, the larger point is astonishing. Part of our defense against disease may come from relatives who vanished from the world. Denisovans were discovered through genetics before a full skull. Most ancient human species were first recognized through bones shaped enough to compare. Denisovans entered science differently. Their identity emerged from DNA extracted from small remains in a Siberian cave. At first, there was no complete skull to study and no full skeleton to display. There was genetic evidence pointing to a distinct human group. This changed paleoanthropology. It showed that whole populations could hide in fragments too small to classify by appearance. Denisovans became a kind of ghost lineage, visible through inheritance more than anatomy. Later discoveries added pieces to the picture, including teeth, jaw material, and more genetic evidence. But the core mystery remains. We know they existed across a wide area, yet their bodies are still poorly understood. That makes them one of the most fascinating human relatives. They remind us that the fossil record is not the full record. Sometimes the deepest identity is written in molecules rather than bones. Denisovan ancestry helps some Tibetans thrive at high altitude. Life on the Tibetan plateau places extreme demands on the body. The air holds less oxygen, and people who are not adapted can struggle badly. Some Tibetans carry a genetic variant linked to efficient response in low oxygen conditions. Research shows that this variant likely came from Denisovan ancestry. That means an ancient human group helped modern people adapt to one of the planet's most challenging environments. The idea is extraordinary. A population that vanished as a distinct people left behind a biological gift suited to thin mountain air. This adaptation affects how the body handles oxygen without producing some of the harmful effects seen in non-adapted high-altitude visitors. It is a powerful example of evolution through interbreeding. Instead of inventing a solution from scratch, modern humans inherited one from relatives who had already faced certain pressures. Denisovan DNA became part of the toolkit that allowed later communities to live where the sky feels close. A girl from Denisova cave had parents from two human groups. One of the most astonishing ancient DNA discoveries came from a small bone fragment belonging to a girl who lived around 90,000 years ago. Her genome revealed that her mother was Neanderthal and her father was Denisovan. This was not a distant trace of mixed ancestry from far back in her family tree. It was immediate. Her parents belonged to two different human groups. The find transformed how scientists imagined contact between ancient humans. Interbreeding was not merely a rare abstraction detected in modern genomes. It happened in real lives, in real communities, in places where different groups crossed paths. The girl is sometimes called Denny, and her existence makes deep history feel suddenly personal. She was not a theory about population movement. She was a child with parents from separate branches of humanity. In one small fragment of bone, scientists found proof that the human family tree sometimes braided together. Ancient DNA turned caves into archives of invisible lives. Caves can preserve more than bones and tools. Under the right conditions, they can hold genetic traces left by humans and animals who once passed through them. DNA can survive in tiny fragments within sediments, even when no visible fossil remains. This has changed the way researchers study ancient occupations. A layer of cave floor may reveal that Neanderthals, Denisovans, or modern humans were present, even if they left no skeleton behind. It is like discovering footprints at the molecular level. The method is especially valuable because bones are rare, fragile, and unevenly preserved. Sediment DNA expands the record by catching traces of presence that older archaeology would have missed. It also allows scientists to track changes across layers of time. A cave becomes more than a shelter. It becomes an archive built from dust, ash, soil, and microscopic remains. The invisible can now speak, and the past has become much harder to hide. Sediment can hold human DNA even without bones. A handful of ancient soil can contain genetic evidence of people who vanished long ago. This sounds almost impossible, but DNA is shed through skin cells, hair, waste, and decomposing material. In cool or stable environments, tiny fragments can cling to minerals and persist. Scientists can sample sediment layers and identify genetic signatures from ancient humans without finding a single tooth or bone. This approach opens extraordinary possibilities. Sites once considered poor in fossils may still hold evidence of occupation. Researchers can detect who used a place and sometimes when different groups appeared or disappeared. It also requires great care because contamination from modern people is a constant risk. When handled properly, sediment DNA turns the ground itself into testimony. Imagine a cave floor that looks empty to the eye. Beneath that surface may be traces of bodies, fires, movements, and returns. The people are gone, but the earth remembered them in fragments. Homo floresiensis lived small on an island of giants. On the Indonesian island of Flores, researchers found the remains of a small-bodied human species that stunned the world. Homo floresiensis stood only around a meter tall. It had lived alongside unusual island animals, including dwarf elephants and large storks. Its brain was small, but stone tools associated with the site suggest capable behavior. The discovery challenged assumptions about what a human species needed to look like. Small size on islands is not unusual in evolution. Limited resources and isolation can shrink large animals over generations. But seeing that pattern in a human relative was startling. Homo floresiensis forced scientists to rethink the diversity of our genus. It was not a miniature modern human and not simply a diseased individual. It was something stranger and more important. On Flores, evolution produced a human form adapted to an island world, proving that humanity's branches could take shapes no one had expected. The Hobbit humans survived on Flores until surprisingly recent times. The nickname Hobbit captured public imagination. But the science behind Homo floresiensis is even more fascinating than the name. This small human species survived until relatively late in prehistory, though exact timelines have been revised as dating improved. Its presence on Flores means that unusual human relatives persisted while modern humans were spreading across wider regions. The island setting may have helped preserve its distinct form. Isolation can protect a lineage from outside competition, but it can also make survival fragile when conditions change. The tools and bones found in Liangbua Cave suggest a long local history, not a brief oddity. For modern people, the idea is startling. At a time that feels close compared with the full sweep of evolution, another kind of human may still have lived in a separate island world. Their story reminds us that the end of human diversity did not happen all at once. Some branches lingered in hidden corners. Island life can shrink large animals across generations. Islands are natural laboratories of evolution. When animals become isolated, the usual rules can change. Large species may shrink because food is limited, and smaller bodies need less energy. Predators may be absent, which reduces the need for great size. Over many generations, elephants can become dwarfs, and other animals may shift in surprising ways. This process is called island dwarfism. It helps explain the strange world of Flores, where small elephants once lived alongside Homo floresiensis. The principle matters because it shows that environment can reshape bodies dramatically. Evolution responds to local pressures, not to a universal idea of progress. A huge animal on a mainland may become much smaller on an island, while some small animals become larger when threats disappear. Islands reveal how flexible life can be when cut off from the wider world. They are places where evolution writes unusual experiments, and sometimes those experiments include human relatives. Homo luzonensis added another mystery to Asia's human story. In Calao Cave in the Philippines, fossils revealed a human relative that scientists named Homo luzonensis. The remains are fragmentary, yet they show a puzzling mixture of traits. Some features look surprisingly ancient. Others fit within the broader human genus. The discovery matters because it suggests that island Southeast Asia held more human diversity than once imagined. Reaching Luzon would have required crossing water because the island was not connected to the mainland by dry land during the relevant periods. That raises fascinating questions. Who were these people? How did their ancestors arrive? What did their bodies look like in full? The fossils do not answer everything, but they widen the map of human evolution. Asia was not merely a corridor for known species moving through. It was a region of hidden experiments, isolated populations, and evolutionary surprises. Homo luzonensis is a reminder that some of the biggest chapters are still represented by the smallest clues. Homo naledi mixed ancient features with a surprisingly recent age. Homo naledi baffled researchers because its body combined traits that seemed to belong to different times. Its skull was small, and some features looked primitive. Yet its hands, feet, and legs had aspects that felt closer to later human forms. Then dating suggested it lived far more recently than many expected. That combination was stunning. A small-brained human relative may have existed, while larger-brained humans were already on the scene elsewhere. The fossils were found deep within the Rising Star Cave system in South Africa, in a chamber that was difficult to reach. This raised intense debate about how the bodies got there and what behavior might be represented. Homo naledi is fascinating because it disrupts simple assumptions. It shows that ancient-looking anatomy did not always disappear early. Different human forms could persist side by side in time, with bodies shaped by their own paths. The past was not tidy. It was crowded with surprises. Rising Star Cave may hold clues about complex ancient behavior. The discovery of Homo naledi in the Rising Star Cave system created one of the most debated puzzles in paleoanthropology. Many remains were found in a deep chamber that is difficult to access. This led some researchers to propose that bodies may have been placed there deliberately. If true, That would suggest complex behavior in a small-brained human relative. Other scientists urge caution. Natural processes, unknown entrances, or repeated accidents must be considered carefully. The debate is important because it touches a major question. What kinds of minds were capable of meaningful treatment of the dead? Rising Star Cave forces researchers to test assumptions about brain size and behavior. Even uncertainty is valuable here. The site challenges the idea that only large-brained humans could do complicated things. Whether the final answer proves simple or astonishing, the cave has already changed the conversation. It asks us to look again at what intelligence can leave behind. Dragon Man sparked debate about a possible Denisovan face. A large ancient skull from China, nicknamed Dragon Man, drew worldwide attention because it seemed to represent a human form close to our own branch, yet clearly distinct. Some researchers proposed that it might help reveal what Denisovans looked like, though that connection remains debated. The skull has a broad face, large brow region, and a striking combination of features. Because Denisovans are known mostly from DNA and fragmentary fossils, any candidate for their appearance becomes enormously important. Still, science moves carefully. A dramatic skull does not automatically solve a mystery. It must be compared with other fossils, dated securely and interpreted within a wider pattern. Dragon Man is fascinating because it sits at the crossroads of anatomy and genetics. It hints that East Asia may preserve crucial evidence for human diversity, but is still poorly understood. Whether or not it proves Denisovan, it gives a possible face to a shadowy world of ancient relatives. Modern humans reached Australia tens of thousands of years ago. The arrival of modern humans in Australia is one of the great achievements of early human movement. It required crossing water into a continent filled with unfamiliar animals, climates, and landscapes. Archaeological evidence shows people were there tens of thousands of years ago, far earlier than many once assumed. This means early modern humans were capable of remarkable planning and adaptation. Australia was never reached simply by walking from Africa across connected land. Even when sea levels were lower, water crossings remained necessary. People had to understand coastlines, resources, and movement across dangerous passages. Once there, they spread into deserts, forests, tropical regions, and coasts. They developed long-lasting cultural traditions tied to place and memory. This chapter shows that early humans were not timid wanderers. They were capable explorers with practical knowledge strong enough to enter an entirely new world. The story of Australia reveals courage, skill, and deep belonging across immense time. Ocean crossings may have begun earlier than scholars once imagined. For a long time, it was easy to picture ancient humans moving only where land allowed. Yet several discoveries have made that picture feel too narrow. Some islands with early human occupation were never joined fully to nearby mainlands, even when sea levels were lower. That means people, or earlier human relatives, sometimes crossed water. These crossings may not have looked like later voyages with sails and maps. They could have involved simple rafts, floating vegetation, or short passages made by people who understood tides, weather, and coastlines. Still, even a short sea crossing changes the story. It requires courage, planning, and enough confidence to leave a visible shore behind. Water is not just distance. It is risk. The possibility of early crossings shows that ancient humans were not merely pushed around by geography. Sometimes they challenged it. The sea, which once seemed like a boundary in prehistory, may have been a route much earlier than expected. The peopling of the Americas was far more complex than expected. Older stories often described a single migration crossing from Siberia into North America near the end of the Ice Age. Today, the evidence points to a richer and more complicated process. People may have moved in several waves. Some likely traveled along coastlines. Others may have followed inland routes when ice opened pathways. Archaeological sites, genetics, and changing dates have turned the question into one of the most active debates in human history. The Americas were not filled in a simple, straight line. Different groups adapted to different environments, and their movements may have overlapped in ways still being uncovered. Each new site can shift the timeline. Each genome can reveal a connection that bones alone could not show. This complexity is exciting because it restores the human scale of the journey. These were not arrows moving across a map. They were families, decisions, experiments, and generations learning whole new continents. Ice Age humans followed coastlines, rivers, and changing animal paths. During the Ice Age, landscapes changed constantly. Glaciers grew and retreated. Sea levels fell and rose. Herds moved as vegetation shifted. Human groups had to read this changing world with close attention. A coastline could offer shellfish, fish, birds, and predictable travel routes. A river could provide water, food, stone, and a natural path inland. Animal migrations could guide movement across open country. These routes were not roads in the modern sense. They were living corridors, learned through experience, and carried in memory. Following them required more than wandering. People needed to know when resources appeared, where danger gathered, and how weather could transform a place. The Ice Age was harsh, but it also created opportunities for those who could adapt. Human movement across the planet was shaped by these shifting lines of water, ice, and life. To survive was to notice patterns, then move with them. Thuringia was once a homeland, not just a bridge. Beringia is often imagined as a narrow crossing between Asia and North America. In reality, during periods of low sea level, it was a vast region of land connecting Siberia and Alaska. It included open landscapes, animals, plants, and human possibilities. For some ancient groups, it may not have been a bridge they hurried across. It may have been a place where people lived for generations. This idea changes the feeling of the migration story. Beringia becomes a homeland in its own right, not merely a passageway between more important places. People could have hunted, gathered, raised children, learned seasons, and developed traditions there. Later, as climates changed and ice barriers shifted, descendants moved into new regions. Much of that ancient land now lies beneath the sea, which makes its story difficult to recover. Yet the idea remains powerful. A drowned landscape may hold the missing middle of a great human journey. Dog domestication may have begun before the first farms. Before wheat fields, pottery villages, or herds of livestock, humans may already have formed a partnership with wolves. The exact timing remains debated, but dogs appear to be the first domesticated animals. That makes the relationship astonishingly old. Early dogs may have helped with hunting, guarding, waste cleanup, or warmth. They may also have offered companionship, which is harder to measure archaeologically, but easy to understand. The process probably began gradually. Less fearful wolves may have approached human camps, drawn by leftovers. Humans may have tolerated useful animals, then favored those with calmer behavior. Over generations, both sides changed. Wolves became dogs, and humans gained an ally with sharp senses and social instincts. This partnership began before the agricultural world transformed human life. It belongs to the older world of foragers, camps, and moving landscapes. The first animal we brought into our story was not raised for milk or wool. It was a fellow hunter. Wolves joined human lives and changed both species forever. Domestication did not simply create a useful animal. It altered the evolutionary path of wolves and humans together. Wolves already lived in social groups. They understood cooperation, hierarchy, attention, and coordinated movement. Those traits made some of them unusually suited to life near people. As generations passed, selection favored animals that could read human signals and remain calm around camps. Their skulls, teeth, coats, hormones, and behavior changed. Humans changed too, because dogs expanded what people could do. A dog can detect scents we miss, hear movement at night, and help track prey across difficult ground. It can warn, follow, learn, and bond. The relationship became emotional, as well as practical. That is why dogs are not just tools made of flesh. They are a domesticated branch of a wild lineage that entered the human circle. Two social predators met, and the meeting reshaped both of them in ways still visible today. Farming transformed human bodies as much as human societies. Agriculture changed how people lived, but it also changed bodies. Farming meant more reliable food in some settings, yet it often narrowed diets. Communities depended heavily on staple crops, which could increase the risk of nutritional deficiencies. Permanent settlements made it easier for infectious disease to spread. Close contact with domesticated animals introduced new pathogens. Skeletons from early farming populations sometimes show signs of stress, dental decay, and changes in workload. At the same time, agriculture supported larger populations and new forms of settlement. It was not simply progress or decline. It was a trade. Humans gained food production, storage, and demographic power, but paid costs in health and labor. Evolution continued under these new conditions. Genes linked to diet, disease resistance, and metabolism faced fresh pressures. Farming did not remove humans from nature. It created a new environment around them. Fields became part of the evolutionary landscape, shaping bodies as surely as forests and plains had done. Lactose tolerance evolved after dairying became useful to adults. Most mammals stopped digesting milk sugar after infancy. Humans are unusual because many adults can drink milk without discomfort. This ability, called lactase persistence, evolved in some populations after people began keeping milk-producing animals. The mutation did not create dairying by itself. Cultural practice came first or developed alongside it. Then biology responded. In communities where milk offered calories, fluid, fat, and protein, adults who could digest lactose had an advantage. This was especially useful in certain environments where crops were uncertain or fresh water could be risky. The trait evolved independently in more than one region, which shows how powerful the pressure became. It is a beautiful example of genre culture evolution. A human habit changed the conditions of survival. Then natural selection favored bodies better suited to that habit. A glass of milk may seem ordinary today, but adult milk digestion carries the memory of herders, animals, and adaptation across generations. Starch digestion increased in some populations with farming diets. Starchy foods became central to many human diets, especially after agriculture spread. Roots, tubers, grains, and later cultivated crops offered important energy. Some populations carry extra copies of a gene involved in producing salivary amylase, an enzyme that begins starch digestion in the mouth. More copies can mean more enzyme, which may help process starch efficiently. This variation appears to reflect long histories of different diets, although the picture is complex. It shows that adaptation can begin before food even reaches the stomach. Digestion starts with saliva, taste, chewing, and chemistry. A mouthful of cooked grain or roasted tuber is already being transformed while it is still being eaten. This is a small but fascinating example of bodies responding to culture and environment. People changed food through cooking and farming. Food then changed people through selection. Even the enzymes in saliva can carry a history of meals eaten by ancestors thousands of years before us. Sickle cell traits show evolution responding to malaria's pressure. Some human adaptations reveal the harsh compromises of natural selection. In regions where malaria has been common, certain variants affecting hemoglobin became more frequent because carrying one copy can offer protection against severe malaria. The best-known example is the sickle cell trait. People with one copy may gain a survival advantage in malarial environments, but inheriting two copies can cause sickle cell disease, a serious and painful condition. This is one of the clearest cases where evolution produces a trade-off rather than a perfect solution. Natural selection favors what improves reproductive survival in a given setting, even if the same variant carries heavy costs. The story also shows how disease can shape human biology. A tiny parasite transmitted by mosquitoes influenced the genetics of whole populations. It is humbling and unsettling. Human evolution has not been guided only by climate and food. It has also been shaped by microscopic enemies. Human evolution did not stop when cities appeared. There is a common idea that evolution belongs only to the distant past. Human beings built cities, invented medicine, and changed the world. So surely evolution stopped. It did not. Evolution continues whenever genetic variation affects survival or reproduction across generations. Cities created new pressures. Dense populations changed exposure to disease. Diets shifted. Work patterns changed. Social structures influenced who had children and when. Cultural tools can reduce some pressures, but they also create new ones. Medicine may help people survive conditions that once would have been fatal, which changes selection in complex ways. Modern life is not outside biology. It is a new biological setting. The pace and direction of evolution are not always obvious, and many changes are subtle. Still, our species remains part of nature. The city street, the farm, and the hospital are all environments. Human evolution did not end at civilization. It moved into rooms, markets, and crowded streets. Culture can change the pressures acting on our genes. Human culture is powerful because it can alter the conditions under which natural selection works. Clothing changes exposure to cold. Cooking changes digestion. Medicine changes survival. Farming changes diet and disease. Social rules change marriage patterns and reproduction. These behaviors do not replace evolution. They redirect it. This relationship is called gene-culture co-evolution, and it is one of the most important ideas for understanding recent humanity. A cultural invention can spread in years, then create genetic pressures that play out over many generations. The body and the learned world become partners in change. This is why humans are so unusual. We adapt not only by waiting for mutations, but by building practices that reshape the problems we face. Then biology sometimes follows. Culture is not separate from evolution. It is one of evolution's most dramatic human tools. Our ideas, habits, and technologies can become forces that shape the future of our own bodies. Ancient migrations mixed populations more often than old stories suggested. Older histories often imagined ancient groups as separate peoples moving neatly from place to place. Genetics has revealed a much more connected past. Populations split, met again, mixed, moved, and mixed once more. Ancient DNA from skeletons has shown waves of ancestry spreading across regions and blending with people already there. This does not make the past less meaningful. It makes it more human. Real communities are formed by encounters, marriages, conflicts, alliances, and movement. The genetic record often shows that identity in one era was built from several earlier sources. Even places that seemed isolated sometimes hold evidence of deep connection. Migration was not a rare exception in human history. It was a recurring feature. People followed opportunity, pressure, curiosity, and necessity. Their descendants carried mixed inheritances forward. The result is that human ancestry is not a set of sealed boxes. It is a long series of meetings, written into bodies across the world. Skin color evolved many times under different sunlight conditions. Human pigmentation is a powerful example of repeated adaptation. As populations moved into regions with different levels of ultraviolet radiation, skin color changed through several genetic pathways. Darker pigmentation helped protect against intense sunlight. Lighter pigmentation could help vitamin D production where sunlight was weaker. But the global pattern is not simple, because diet, migration, and local history also mattered. Similar skin tones can arise through different genetic combinations. Different skin tones can exist within regions because ancestry and environment interact in complex ways. This is important because it shows how shallow social categories are when compared with biology. Skin color is visible, but the evolutionary story behind it is layered and practical. It is about sunlight, nutrition, protection, and survival. The same human species adapted again and again to different skies. Pigmentation is not a sign of separate kinds of people. It is evidence of one species responding beautifully to the planet's varied light. Blue eyes may trace back to a shared ancient mutation. Eye color can feel deeply personal, yet some variation may have a surprisingly specific history. Blue eyes are linked largely to a regulatory change affecting how much melanin is produced in the iris. Researchers have suggested that many blue-eyed people share ancestry connected to an ancient mutation. The trait likely spread through population history and perhaps social selection, although the exact reasons remain debated. What is fascinating is how a small genetic change can alter appearance so noticeably without changing the eye's basic function. The iris becomes lighter because pigment is reduced and light scattering creates the blue effect. There is no blue pigment painted inside the eye. It is a physical effect produced by structure and light. This makes eye color a quiet lesson in evolution. A tiny inherited variation can become part of identity, beauty, family resemblance, and ancestry. Every gaze carries biology, but also the long history of chance. Wisdom teeth became troublesome as jaws and diets changed. Wisdom teeth made more sense in mouths that faced heavier chewing and greater tooth wear. Over time, human diets changed, especially with cooking, tools, and later agriculture. Food often became softer and easier to process. Jaws also became smaller in many populations. The third molars did not always disappear at the same pace. The result is familiar today. Wisdom teeth can become impacted, crowded, painful, or difficult to clean. This is not poor design in the simple sense. It is a mismatch between inherited anatomy and changed conditions. Evolution often leaves such mismatches because body parts do not all adjust together. Some people never develop wisdom teeth at all. Others have enough room for them without trouble. The variation shows a process still unfolding. A dental problem in a modern clinic can therefore connect to deep changes in food preparation and jaw growth. Even an aching molar can tell a story about human history. Human chins are strangely rare among our closest relatives. The human chin is more mysterious than it seems. Many animals have lower jaws, but the distinct projecting chin of Homo sapiens is unusual among our closest relatives. Neanderthals did not have chins like ours. Earlier human species generally lacked the same shape. Scientists have proposed many explanations, including chewing forces, speech, facial reduction, and developmental changes. None has settled the matter completely. This makes the chin fascinating because it is so ordinary and yet so difficult to explain. It sits on every modern human face as a small signature of our species. One possibility is that the chin emerged as the rest of the face became smaller and tucked back beneath the skull. In that view, it may be partly a consequence of broader facial change rather than a feature selected for directly. Whatever the final answer, the chin reminds us that even familiar anatomy can hide unresolved evolutionary questions. Goosebumps are leftovers from fur-raising ancestors. When you feel cold or startled, tiny muscles at the base of hair follicles can contract. The hairs lift, and the skin forms little bumps. In furry animals, this response can trap insulating air or make the body appear larger during threat. In humans, with our reduced body hair, the effect is much less useful. It remains as a leftover from ancestors for whom raised hair mattered more. This is called a vestigial response, though it has not vanished completely. The sensation can also appear during strong emotion, especially music, awe, or fear. That connection shows how ancient body systems can be woven into modern experience. A chill during a song may involve machinery once tied to warmth and defense. Goosebumps are therefore not just a quirky reaction. They are a small performance of evolutionary memory. The body briefly behaves as if it still wore a thicker coat from a much older world. Tailbones quietly reveal that our lineage once had tails. At the base of the spine sits the coccyx, a small structure made from fused vertebrae. It is the remnant of the tail. Our distant primate ancestors had tails, as many primates still do. In the ape lineage, external tails were lost, but the internal trace remained. The coccyx is not useless. It serves as an attachment point for muscles and ligaments involved in pelvic support. Still, its origin tells a deeper story. Human bodies are not built from scratch. They are modified versions of older bodies. Evolution edits what already exists. The tail was reduced, repurposed, and folded into a new anatomy. That is why a person can sit on a structure that carries evidence of an ancient tail without ever noticing its history. The coccyx is humble, easily ignored, and sometimes painful after a fall. Yet it is one of the clearest reminders that our bodies are archives. Ear muscles remain from ancestors who could swivel their ears. Some people can wiggle their ears, but even those who cannot still carry the muscles involved. In many mammals, external ears can rotate toward sounds. This helps locate predators, prey, or social signals without turning the head. Humans mostly lost that ability as vision, head movement, and other forms of attention became more important. The muscles remain, but they are weak and usually under poor voluntary control. They are another example of evolutionary leftovers. The body keeps traces of functions that mattered more in earlier ancestors. Interestingly, studies show that these muscles may still activate faintly when people listen closely to sounds in different directions. They do not swing the ears like a cat's, but the old system may still twitch beneath awareness. This makes the human ear a small museum of attention. It remembers a time when survival depended more on turning toward rustles in the dark, with mobile ears. The appendix may still help support useful gut bacteria. The appendix was once often described as useless, but that view has softened. This small pouch attached to the large intestine contains immune tissue and may help maintain communities of beneficial gut bacteria. One idea is that it can serve as a safe reservoir, allowing helpful microbes to repopulate the gut after illness clears them out. This does not mean the appendix is essential for everyone. People can live without it. It can also become inflamed, which can be dangerous without treatment. But calling it pointless misses the complexity of biology. Evolution often preserves structures that have modest or context-dependent roles. The gut is not simply a tube for food. It is an ecosystem filled with microbes that influence digestion and immunity. The appendix may be part of that hidden management system. A small organ once dismissed as a mistake may actually reflect the ancient partnership between humans and their internal microbial world. Human feet are arches built from an ancient climbing past. The human foot is a masterpiece of compromise. It carries the legacy of grasping primate feet, yet it has been reshaped for upright walking. The big toe aligns with the others rather than sticking out like a thumb. The arches help absorb impact and store energy with each step. The heel is strong. The toes are shorter than those of many climbing primates. Together, these features create a platform for efficient movement on the ground. But the foot still carries hints of older ancestry in its bones, tendons, and flexibility. It is not a wheel, a hoof, or a simple block. It is a transformed climbing structure pressed into service as a walking engine. Every step depends on that history. The arch rises, the heel strikes, the toes push away. In that smooth motion, an ancient tree-capable body has become a traveler's foundation, carrying humans across continents one footprint at a time. Our backs still struggle with the price of standing upright. Back pain is common partly because upright posture placed unusual demands on an inherited spine. Our ancestors did not evolve from creatures with bodies designed like pillars. They came from primates whose spines were shaped for different patterns of movement. As bipedal walking evolved, the human spine developed curves that help balance the head and trunk above the hips. Those curves are essential, but they also create stress points. The lower back carries significant weight. Discs compress. Muscles must stabilize the body during bending, lifting, sitting, and walking. Modern habits can intensify the problem, but the underlying challenge is ancient. Standing upright freed the hands and changed the course of human evolution. It also left the body with a balancing act that never fully disappears. The ache someone feels after a long day is not just personal discomfort. It is a reminder that every evolutionary advantage can bring a cost. Knees became remarkable shock absorbers for life on two legs. The human knee carries huge responsibility. It must support body weight, bend smoothly, stabilize movement, and absorb repeated impact. In bipedal walking, each leg takes turns carrying the whole body. That makes the knee central to efficient travel. Human knees angle inward slightly from the hips, helping place the feet beneath the body's center of gravity. This reduces side-to-side sway and makes walking more economical. Cartilage, ligaments, tendons, and bone surfaces all work together to manage force. The system is impressive, but it is also vulnerable. Injuries, arthritis, and wear are common because the knee operates under heavy mechanical demands. Evolution shaped it well enough for survival and reproduction, not for perfect lifelong comfort. Still, every step shows its brilliance. A joint that seems ordinary is constantly calculating pressure through structure. The knee helped make long-distance walking possible, and long-distance walking helped make humans a planet-crossing species. The pelvis records the compromise between movement and birth. The human pelvis tells one of the most important stories in our skeleton. It had to support upright walking, anchor powerful muscles, and allow childbirth. These demands did not always point in the same direction. A narrow structure can make movement more efficient. A wider birth canal can ease delivery of large-brained infants. Human evolution balanced these pressures in a complex shape that differs from earlier apes. The pelvis is bowl-like, supporting internal organs above legs that move beneath the body. It helps transfer weight during each step. At the same time, it forms the passage through which newborns enter the world. This dual role makes it one of the clearest examples of evolutionary compromise. It is neither perfect for locomotion nor simple for birth. It is a workable solution shaped by competing needs. In the pelvis, the history of walking and the difficulty of arrival meet in bone. Ancient humans adapted to deserts, forests, coasts, and frozen plains. The success of Homo sapiens rests partly on an astonishing ability to enter different habitats and learn their rules. A desert demands knowledge of water and heat. A forest demands attention to plants, animals, and hidden movement. A coast offers tides, shellfish, fish, and storms. A frozen plain requires warmth, planning, and skill with seasonal resources. Human bodies helped, but behavior made the difference. People made shelters, clothing, tools, containers, and food strategies suited to local conditions. They learned from elders and adjusted through culture. This flexibility allowed one species to occupy environments that would defeat a more specialized animal. The same basic human body could survive under blazing sun or near glacial cold because knowledge filled the gap between anatomy and challenge. Adaptation was not only genetic, it was practical, social, and inventive. Humanity spread widely because people learned how to belong to places their bodies had not been born for. Climate swings repeatedly pushed human evolution in new directions. The environments of human evolution were not stable backdrops. Climates shifted again and again. Wet regions dried. Grasslands expanded. Forests retreated. Lakes appeared, vanished, and returned. These changes affected food, predators, shelter, and migration routes. A lineage that survived had to cope with uncertainty. Some researchers argue that environmental variability favored flexibility because rigid specialization becomes risky when conditions change. This may have encouraged broader diets, movement, cooperation, and innovation. Climate did not act like a single, simple cause. It created changing pressures that interacted with anatomy, culture, and chance. Fossils found in different layers often reflect worlds unlike the ones before or after them. A species could thrive for a time, then face a transformed landscape. In this sense, human evolution unfolded under a restless sky. The planet kept changing the questions, and ancient humans survived by finding new answers. Our adaptability may be a legacy of instability itself. Extinction removed many human branches before ours remained alone. The fact that only Homo sapiens survives can make the outcome seem inevitable. It was not. Other human groups lived successfully for long periods before disappearing. Some may have been absorbed partly through interbreeding. Some may have declined because of climate change, small population size, competition, disease, or bad luck. Extinction is rarely caused by one neat event. It often comes through accumulated pressure. A group can survive one harsh century, then fail when several stresses arrive together. The disappearance of other human forms left our species alone in a way that is unusual compared with much of the past. That loneliness should not be mistaken for superiority. It may reflect timing, geography, numbers, and chance as much as ability. The vanished branches mattered. They were not practice versions of us. They were real populations with their own histories. Their absence gives modern humanity a strange inheritance. We are surrounded by relatives only in fossils and genes. The human story is written in bones, genes, tools, and footprints. No single type of evidence can tell the whole story of human evolution. Bones reveal anatomy, growth, injury, and relationship. Genes uncover ancestry, interbreeding, migration, and adaptation. Tools show planning, skill, and changing behavior. Footprints preserve movement in a way that feels almost alive. Each source has limits. Bones may be fragmentary. DNA may decay. Tools may not identify their makers. Footprints may capture only one brief moment. Yet together, they form a powerful record. The past becomes clearer when these clues overlap. A fossil can show a body. A genome can reveal relatives. A stone edge can show action. A trackway can show presence. Human evolution is not preserved as a complete book. It is scattered across caves, sediments, deserts, riverbeds, and museum drawers. Scientists read it piece by piece. The wonder is that any of it survived at all. From broken traces, an immense story has begun to return. Humanity is still evolving, quietly, generation by generation. Evolution is not finished with us. It continues in small changes across populations as mutations arise, environments shift, and patterns of survival and reproduction change. Some modern pressures are ancient, such as disease. Others are new, such as altered diets, medical care, urban life, and delayed reproduction. Many changes are subtle and hard to predict. Evolution does not move toward a perfect future. It responds to conditions in each generation. Culture now plays a huge role, buffering some pressures while creating others. Technology may change which traits matter, but it does not remove us from biology. Our genomes still carry variation. Our bodies still interact with the world. Our descendants will inherit not only our genes, but the environments we shape for them. The idea can feel humbling. Human evolution is not only a story behind us in caves and fossils. It is also unfolding now, softly and continuously, inside the living stream of humanity. And so, we come to the end of our journey through the long and astonishing story of human evolution. We have followed the trail back through ancient bones, buried tools, changing bodies, and vanished relatives. We have seen that humanity was never a simple ladder rising neatly through time. It was a wide and branching story, full of experiments, crossings, disappearances, and unexpected survivals. We have met ancestors who learned to walk upright beneath changing skies. We have seen how fire, language, culture, and cooperation helped fragile bodies become remarkably adaptable. We have glimpsed Neanderthals, Denisovans, island humans, and other lost branches whose traces still whisper through fossils and living DNA. And now, after all that deep time, here you are, breathing softly, resting in the present, carrying, within your body, a story older than memory. There is something calming about that thought. Every heartbeat belongs to a chain that endured ice, hunger, darkness, distance, and uncertainty. Every breath is part of a living thread that reached this moment, quietly and patiently, through countless generations. If you enjoyed this sleepy journey through history, you're very welcome to like, subscribe, or leave a thought below. It helps others find their way here too, one sleepy soul at a time. And if you happen to still be awake, there should be another video waiting on the screen now, ready to carry you into another calm corner of the past. But for now, there is nothing more you need to do. Let your shoulders soften. Let your breathing slow. Let the long story of humanity fade into something warm and distant. The bones are resting. The ancient paths are still. And the night can hold the rest. Sleep well, and good night.